cutting-edge 1 gigawatt hour electrode production in Europe. Today I'm here at Creonia Cells. Join me for a really packed video on battery manufacturing and what they call the next generation of batteries. And it might be a bit different than what you might think. So join me, let's go. Hi Marcus.
Hello, good morning.
Good morning, good to see you again.
Yeah, good to see you here at the site, or almost at the site, yeah.
Exactly, no, I'm really excited. I think today we're going to have a really packed day.
Yeah.
Looking at your manufacturing, looking at new facilities, and really get a hands-on experience of what you're exciting building here in Austria.
Yes, I'm looking forward to having you here, and I want to show you our technology and what are the benefits, and you're welcome here. And let's go.
Let's go. So Marcus, maybe for our audience, where are we right now?
We are right now in Upper Austria, part of Austria, right between Salzburg and Vienna, next to Linz. And I picked you up here now in Enns, the oldest town of Austria, where the Romans already settled, and now we're on our way to our site, just a few minutes to drive.
Amazing, and I think so very for our audience, because we have quite a global audience, so we're quite in Central Europe right now, which I think is really exciting because we talk about a lot on battery manufacturing, of course, especially in Asia and many other regions. But I think, building technology here in Europe is also quite exciting. So you want to see what you're kind of doing right now?
Yes, you're right. So in Austria, it's not quite common to do development on electrode manufacturing. So there are a lot of activities now in making packs, but not electrodes.
Yeah, which of course is an important component, especially for the full battery value chain. And that's something also which excited me actually when I met you the first time and I saw your facilities back then. So again, very excited to see what happened since then. I think, as you already kind of mentioned, I think there's been some developments.
Yep.
But as someone, of course, spent a lot of time also in chemistry and research labs, etc. But to really look at how can you scale that, and really, I remember you showed me some early samples. I'm excited to newer samples, and really seeing how what kind of scale can you achieve in your production.
Yes, you're right. So making coin cells in the lab can be quite a fast process, but then scaling up is the hard thing, I think. Yeah.
But you're process engineers, right? So you understand scaling, and that's what really got me excited.
I'm not really a process engineer, but I'm a chemist, technical chemist. So my background is chemistry, and I learned a lot during my former professional career at Evonik in process management, in thinking in systems, and making roll-to-roll processes for fibers, films, and membranes, and all this I can now apply in developing the process now, the Creocell process, the Creocell electrode manufacturing process. Yeah, we are right here now. So this is you see now the labs behind and our technical center here, and we just rented part of this building here in 2020, starting with a small room and then increasing the size, the number of labs, also our offices, and I'm happy to have you here, and let's go in.
Let's do it. Excited to see it again. Marcus, thanks so much for having me. I'm really excited to see it again in person, Creonia Cells. So maybe if you can start by what can we actually see today?
Yeah, welcome again. Actually, we are in our technical center, and I want to show you the labs today. I want to show you the cells, what we're preparing the electrodes, how the process looks like, how the benefits are of our technology. Yeah, let's come in and show how the cells look like where we are right now with our technology.
Absolutely. And of course, you as an audience, you don't know it yet, but you see some big equipment here, which we're going to look at a bit later. So please stick around, because we really want to show you how these cells are made. And already as a bit of a hint, that's quite a unique process. So I've seen quite a few production lines. This is something quite unique, so you don't want to miss out. But maybe one thing for the listeners who don't know it yet, like, why did you start this company? What's the history? What's the story?
Yeah, the story is that a couple of years ago I thought that the state-of-the-art manufacturing process, where you boil off a lot of solvent, use a lot of energy, huge capex and so on for the electrode manufacturing machine. This must go simpler, and I had the idea to do it differently, and this is what I want to show you today, to make single freestanding electrodes. We call it the Creonia Cell electrodes, and we also show it that we can make it not just single layer but also triple layer, where anode, separator and cathode is made in one step. And this enables us to make unique cells in the future.
Absolutely. And again, I know you're excited to see it, so let's go inside and see one of the first labs. So what's quite nice today is we can really open up all the Pandora's box. So they let us look at all the different R&D labs, but also manufacturing facilities. And as a first step, we want to look a bit at the technology. So I think we're going to go over there.
Helen, please. So we have here a pouch cell, a standard pouch cell, and our new bipolar stack. Please, Helen.
Yes. As already mentioned, on the left-hand side you can see one of our standard pouch cells, which is produced with our electrodes. This already shows certain advantages over commercial systems. And additionally to that, we developed a so-called bipolar stack, which you can see on the right-hand side here. I will now demonstrate the differences by measuring the voltages. So when we look at the first one on the left-hand side, we can see here that we have the standard 3.2 volt. 3.28 volt. And on the right-hand side, if we measure over the entire cell, we can see over 9.8 volt, which shows us that here we have 3 cells serially connected within one cell, which is the next generation battery system.
Amazing. Well, thanks so much, Helen. Thanks for showing that. Maybe there's some models there as well.
Yeah.
Maybe you can show
here we
that
can
too.
clarify that a little bit more. So the battery on the left-hand side is the standard parallel stacked battery, which adds up to the standard 3.2 volts, whereas on the right-hand side, these cells are serially stacked, so we can get the full voltage of all the connected cells instead within one cell, which saves cost and material and also has grammatical benefits.
So the tri-layers I mentioned before, they are stacked on top of each other, and so therefore the voltage is added.
Very good. And it's exciting because also I've seen there's a range of patents out there. Maybe some people have read about bipolar, because quite a few other companies are also working on that, right? I think Toyota is one of them and others. So I think it's quite exciting and seeing this here being built now.
Helen, you can also show the single voltages of...
Yeah, sure, of course. So here when we look at every single cell, we can see the standard voltage. First one, second one, and third one, to show that they're all working independently as well.
Yeah.
Perfect.
Simon, curious how we make it?
Yes, let's do this.
Let's go to another lab and I will show you how the electrodes look like and what is actually inside these cells.
Let's do that. Perfect. Thanks. Thanks, Anna.
Thank you.
So after seeing a cell and seeing a bit of like how this looks in theory, now we want to look at these electrodes in real. And Marcus, maybe you can start us off. What are we seeing here?
Yeah, this is the cell we've seen before in the other lab. And the ingredients here are made of these freestanding electrodes. So we have single processes. Simon here, this is an anode of carbon, graphite in there. And this is the LFP cathode. So, and you maybe wonder how the current collectors will be applied to this system to bring the current in and out. And we have developed some lamination processes. Here you see a double-sided LFP cathode with 4 milliamp hours per square centimeter loading. And This is then the corresponding anode to it.
You can of course see the copper for aluminum for.
Yeah, exactly. And this one is suitable for standard parallel stacking of this cell, where we have the 3.2 voltage here. And in between all of these electrodes, we are using currently a standard commercial polyethylene, polypropylene separator. And everything is in electrolyte. Yeah? One big advantage is that we can make the loading even higher. So this one is, for example, an LFP cathode with 8 milliamp hours per square centimeter. It's quite heavy.
It's quite heavy, yeah. I mean, it's hard to see it on the camera, I'm sorry, but you can trust me, this heavy if you could lift it.
So this has even more advantage, so you can increase the storage capacity by saving aluminum, the dead material in there, and you can also do this with the anode. And in addition, we can tune the porosity in the first layer and in the second layer independently, and therefore influence the diffusion behavior, for example, in the cell at high power, for example.
And now I see already like there's a separator, you already mentioned it. It's not something you're producing right now, but I think there's something quite unique producing. I think, Helena, maybe if you could share a bit more about what this one other sample is, because I think that's the one. I remember I saw this at an expo before, and a lot of companies got very curious about this one, so we want to hear more about that one.
Yes, of course. So I'll show you first. This is our multi-layer system with the anode on top and the cathode here. And yeah, as mentioned earlier, we have a multi-layer system where the separator, the anode and the cathode are produced in one go. And that has many advantages. On the one hand, we can produce the normal single standing electrode foils, but also the multi-layer systems as earlier shown in the bipolar stacks.
And as it can hardly be seen by the eye, we need a microscope to show you how these 3 layers actually look like. And please, Simon, have a look into the microscope and look into it. Simon is now looking at the tri-layer system, and in the back on the screen we have an example of a multi-layer system where we stack many tri-layers on top of each other. So you see here the dark one is the anode, then you have the white one is a separator in between, and this one is the cathode, and it's not hard, it cannot be seen. There is an adhesive in between here. And if you do this, you can also add a conductive separation layer in between. Then you end up with this 15S stack, which will give 48 volts immediately. Very small, very compact, no wiring. You can use it, put it in a protection foil and use it.
Thanks for sharing. I think that's also quite unique. Again, hopefully you can see this as well.
You can also show how it bends. It's really stiff.
You want to show it?
Yeah, I would like to show it. If you can, I don't know if you can see it, but you can really apply some force and it stays super compact and stiff, which has many advantages.
You can also use it as a structural part, for example, in any housings or whatever.
That's super cool. And I think it's also good to see this kind of more like on a structural level. And I think that's quite unique, these kind of layers you're building here. Mm-hmm. So that's really fascinating. Yeah. But of course, that's all really nice. But like, how do you make this, right? So we kind of looked at the full cell. Now we kind of get a bit of an understanding of some of the layers, the electrodes. But what's actually the material? Like, what are we putting together? And I think as a next step, we want to see the slurries and how you measure the slurries, right?
Yeah, okay, let's go. So Carolina has prepared some slurry here, and she's doing the measurement of the viscosity, which is quite important for our process. And please, Carolina, show how the slurry looks like when it flows into the tube here. Yeah, she's now mounting the pipe in the viscosimeter, and then everything is brought to the appropriate temperature in the water bath. So you have to wait now a couple of minutes until the temperature is adjusted, and then there is a rotating cylinder in there, and the force is measured, and therefore the viscosity can be calculated.
Why is it so important to know the viscosity of that?
It's in our process outside, we'll show you later. So we have pumps, we have filters, we have extrusion units, slot dies, where we extrude them, and therefore the adjustment of the viscosity is very important to get a very good uniform trilayer system.
And then as a next step, so once you understood you have a good slurry, you want to get to the mixing and to the coating.
Yeah, so in the lab we are starting with the mixing, and Selma is showing you how the mixer looks like and how the slurry looks like in the mixer, and then she will prepare some electrodes in the A5 size, and then you will see how simple it is to make the electrode, a freestanding electrode.
Okay, so let's look at the lab scale before we go to the bigger scale. And that's already, I know, behind us in the window over there. It's a bit of a sneak peek, so yeah, let's go to the next step.
Okay, come. Don't disclose too much secrets.
Okay, so now we want to understand how we actually make these slurries and what these slurries can be made of.
Yeah, so Creonia is right in front of the hood, and this one is our small lab mixer capable of making about 1 liter of slurry, and she winds up now, and then you can see how the slurry looks like, how it pours into the vessel back, how the viscosity looks like, and this is actually now an LFP slurry in a solvent, but depending on the binder, we can use different binders, and we can also then use different solvent systems, and this is a platform technology, so we can also use different chemistries, not just LFP but also NMC, different newer materials like the LFMP, for example, all kinds of NMC materials, but also on the anode side, starting from graphite, different binders, adding some silicon. Everything is possible, has to be developed, but in principle everything is possible with this slurry.
So really flexible, as you said, on different technologies, and also I guess potential partnerships and other kind of technologies you can incorporate into your manufacturing process.
Sure, if there's somebody developing a new chemistry, a new powder, also for example sodium ion in future, or if we change the binder to some polyelectrolytes, then we can go even to solid state systems, for example. So it's a very versatile technology we can develop in any direction you want.
Perfect. So as a next step, we want to look at the other hood. Thanks so much, Carolina, on this. And then now we want to see, that brings me back to my PhD days, so really thank you for that. Yeah, I did a lot of this in the lab, a lot of coating, so Selma, really excited.
So you're familiar with it?
Yeah. I had to do this, but I'm sure you're going to do way better than I did. But if you can show us, please.
Yes, Selma, please.
It's actually pretty easy because, like you said, everybody is very familiar to this process, and we just prepared the slurry there, and we just took in the solvent, and we just do doctor blade to cast the slurry on this glass plate, and now I'm doing it. It's not a perfect one.
Yeah, so instead you cast it on aluminum or on a copper foil like you did probably. Yeah. We use just a glass plate where we cast it on, and then right after casting we just put it into a liquid.
And we simply put into the liquid instead of the drying in an oven and having solvent vapor in the air everywhere, and we just simply put into the liquid in this case we use just pure water, and as you can see it's shaped very quickly, and it can be taken out of the water so easily. And we avoid the solvents vapor also. It's
Yeah. And from here on, you see it forms rapidly, quickly. The surface is solid, so it can touch any rollers in the process. And later on, we just wash it and dry it.
Yeah. I mean, I can definitely say it's a quick process. That's good. I remember when I had to dry my electrodes for like hours and hours in the ovens and things like that.
Yeah.
This was really, I would have loved this kind of quick process for some of my electrodes in my PhD.
So, ready for drying, open the oven. It's very simple.
Okay, cool. Well done. And I'm really excited because I think one of the next steps you're going to show us how this is done in a bit of a bigger scale.
Yeah, so we need to have a roll-to-roll process to apply it in a technical process, and that's what we have developed last year. And therefore, I would like to invite you to go to our technical center, to go to our lab line, where we have started. And this lab line has a width of 15 centimeters in the web, and I will show you the process.
Absolutely, and I think you don't want to miss out on this because I think that's really exciting. So now we saw a bit of the process, a bit of what happened before, but now we're really talking about manufacturing, and I think that's what most of you are here for. So let's go to the next step.
Yeah, and manufacturing is the hard thing.
It is the hard thing, and that's think, yes, and a lot of people do this in their PhDs and their labs, but to really build at scale, not that easy. So thanks so much, Selma.
yeah. See you.
Thank you. Please come in.
Okay, so now this is more like it.
Yeah, so this is what we started in 21 with the lab line in the back of Simon here. And I want to show you a little bit the process now. And so it starts everything with the slurries. We bring the slurries here. We have standard batch processes like everyone has, where we make the slurries in a 30-liter scale. And from here on, we have anode separator and cathode slurry, and we have 3 pumps here, and we pump it into our black box. There are some ingredients in there, some magic components we don't want to show yet, which enables us to make very smooth, evenly distributed membranes, systems, electrodes, tri-layers, yeah.
But Marcus, you tell me this is a black box. It is a black box, but is there anything you can share? What's in there?
Yeah, it is actually a black box. We do not want to share too much, but one thing we can show you from outside are the slot dies we are using, and I would like to hand over to Klaus, who shows you the slot dies we are using.
Yes, that's a standard slot die we use for single layer extrusion. Here we use spacers to make the gap in between the nozzle, and that's our proprietary 3-fold nozzle where we produce our tri-layers. So it can extrude the cathode separator and anode in one step, and that's our core competence.
Amazing. So something like this is in there, and then probably something else.
Exactly.
You're right.
Let's dig into this. I guess if you want to see more, visit them and be very nice. Maybe they show you a bit more.
After an NDA.
So yeah, but I mean, it's good. You have to come here. It's a nice place. So perfect. No, thanks for showing this. And now we want to understand a bit more about the line.
Yeah.
So let's walk through this.
Okay.
Okay, now we really want to understand a bit this mini pilot line you have here. So where do we start, Marcus?
Yeah, so after our magic path behind there, the black box, we are now seeing the baths here where the washing is done. And Marcus, please explain a little bit closer what we can see here, what we are doing.
Yeah, as you have heard already, our foil is solid very fast after the extrusion in water, and here we wash out the solvent. And the benefit is that that it goes up and down here and can go up and down in the washing baths to extract very quickly all organic solvent from the electrodes, and it moves farther cascade by cascade. It's washed until it's free from solvent, and it has only to be dried from water with air. We move forward to our dryers, which in this case it's all self-made, that we can make very quickly and customized samples for lab scale and for prototypes.
Yeah, maybe what important is also that every solvent we are using stays in the liquid, does not go into the drying step, and therefore we have an environmental advantage over the state-of-the-art technology, and we can recycle the solvent and reuse it again in the slurry preparation.
Great.
And this is also very energy efficient when we just dry off the water, in this case, not the liquid.
What do we see here?
So these are the dryers here. They are very small drying ways here, or lengths, but it's enough for prototyping, and in the end here the dry membrane, the dry electrode comes out, and this wound up here again.
And that's quite nice. I mean, this is a good size. I think, I've seen other prototype labs. I think that's a good starting size, and smaller ovens, and I'm excited to see, of course, how we can do this bigger.
Yes, sure. So this is suitable size for making small pouch cells, small coin cells, and whatever.
Yeah.
And it demonstrates that the process is working. But for Series A or whatever productions, we need something bigger and more professional. And that's why we have invested also in a pilot line, which we're going to show you right now.
You already get a bit of a feeling behind us. You see some big things there, but just to kind of put it also into perspective, right? Just a bit earlier we saw it done by hand, single sheets. That's already nice work. A lot of people do this in the lab, in the research labs, etc. This is a massive step up already. The output you can create compared to how many layers you would have to do by hand already here in a roll-to-roll process. But now we want to go to the gigawatt hour scale.
Yeah,
so
this is already megawatt hour scale.
Yes.
If we would run it 24/7 at 10 or 15 meters per minute,
Yes.
which this plant is capable of.
Yeah.
And this one over here is almost capacity of 1 gigawatt hour if we run it 24/7. And for this very small compact machine I'm going to show you today,
Yeah.
it's really, to my opinion, impressive.
Let's do that. Let's go to the next one. I think we're going up potentially.
Yeah, so I do not climb up there, but you can take now an overview of the plant from top down, and then we meet again at the beginning of the line and go through it.
Let's do that.
Yeah.
Thank you both.
Okay, well, Simon, have you got a good overview from the top of the dryer?
I would say so.
Yeah?
Yeah.
Then let's look into more details. So the black box again here is where the magic is in there, and we covered it, but from here on, where the washing bath is, we can show you how it looks like in a pilot line scale with 1 gigawatt hour of capacity. We have just the web for demonstration purposes in there, and we'll show you how deep the baths are and how good the washing is.
So we can see, if we compare this, right? I mean, as I say, it's kind of a thin line right now, but you can go much wider now than you can go over there.
Yeah.
Marcus?
Yeah, as we already heard, this is very quickly. It's solid, our electrode, and this allows us to move it on rolls during the drying. In comparison to the wet process, where it's in a air dryer, which is very big and very expensive and needs a lot of energy. Here we can move out the solvent with water, and we can also move it from up and down to save space, which makes the process machinery compact and the process less expensive in equipment and also in energy costs and energy amount necessary. You can look in here, it's for this pilot plant, it's 1.5 meter deep, where the electrodes goes up and down. Here is just for showing you the basic principle is a demonstration electrode in it, because we are still in ramping up the process on this pilot scale, but you can see the basic principle that here you have a lot of meters, a very compact way to finally finish the electrode before it goes to drying off the remaining water, while the solvent remains in all the washing water. You can move on.
Yeah, Simon, what do you think of this pilot line of the scaling up?
It's impressive because I remember the first time I saw the mini line. So now to see the pilot line, and I think, which is kind of cool, is like, you know, the way kind of how you put things which tend to be quite big and try to make them smaller. I think I really appreciate from a footprint. We see a lot of development in the factory landscape is, you know, any space is expensive, and I think we have even seen other factories trying to cut out a meter of the, you know, of the ceiling, which already reduced from the cooling and all these different things you need. Yeah. So I think finding ways how you make things compact and you go not just horizontal but also vertical is really cool. Yeah. And I think one next step here is the drying.
Yeah, exactly. So come here over again after the washing bath. We then hand over the web to the dryer. Here in the dryer we have a demonstration electrode in there too, just to see how it works.
So we move on to our dryer, which is inside of this box, and Markus will now highlight our benefits and the main points of the drying process, while I will open the dryer itself.
Yeah. So as Markus mentioned before in the washing bath, the same advantage of the ups and downs of the winding is also suitable for our drying process, and we also have just a demonstration web here. If you see a closer look here, that it's going up and down here, up and down, and on a very short space here we have at least 30 meters of drying length, and therefore a lot of residence time, which you would have usually just in a very long oven in the case of the slot of the wet coating process.
Yeah. Absolutely. And are there like any other benefits? So like space, of course, an obvious one. Is also energy-wise.
Sure. So all the solvent is in the water. We do not have to dry off solvent, so we do not have to take care about any flash points, about any taking out of the solvent again of this huge gas flow, and this, therefore, it's much more energy saving. The water can be taken out very in a concentration form, and the energy can be kept back and recycled in the drying step. And therefore, we assume that we save up to 80% of the energy compared to the wet coating process.
That's a really impressive number. And kind of also another thing is, so what kind of energy are you using? Is it like electric heaters? Is it gas?
No, this is regular electric heating from renewable energy. No gas is needed at all, because we are drying at moderate temperatures just to evaporate the water.
Very cool. And is this possible also, because I know some other companies doing it for the anode side, right? They've got like, you know, water-based processes. But I think you also mentioned LFP and NMC, so can you also make cathodes this way?
Yeah, sure.
So why can you do it but not the other ones? Trying.
Because we have a freestanding electrode, which has a solid surface right after formation in our first bath, and any winder, any roll does not harm the surface, and that's why we can save such a lot of space here. And in the standard process, you have a sticky surface almost half of the machine until you can wind it up and down.
This is also quite, this is the entire drying here, right, I'm seeing?
Yeah, that's all.
Because if you think about this, I mean, again, you ever should visit like a traditional production line, these ovens are massive. And if you say now you can get 1 gigawatt hour only from this small box, that's really impressive, right?
Yeah.
Plus the energy saving. So I think that's very exciting to see.
Okay.
Yeah.
And the rest is the winding again, which we've seen over there. Nothing new to see.
Cool. So let's go to the next step, which I think is the calendaring.
Yeah.
Control the process.
Finally, I want to show you how we do the laminating on the copper and on the aluminum foils, the double-sided.
Absolutely. Let's do this too.
Yeah.
Thanks.
Our lab calendar, and here we want to show you now the calendaring on the aluminum foil of the cathode, and therefore I'm gonna call the colleagues and they will show you. Well, Simon, and now we want to show you how we put the electrodes on the copper and the aluminum collector. In this case, the aluminum double-sided electrodes with LFP, 4 milliamp hours per square centimeter. And please, Marcus, show Simon how we do this.
Yeah, Simon, hello. I prepared the bridge between the wet coating process and our extrusion process for you to show now. Here you see 4 milliampere per square centimeter cathodes, which are rather thick, which is also a comparative benefit of our process, with a pre-coated aluminium foil, and this we will now in one step calender under heat and pressure to the freestanding to the electrode with current collector in our lab scale calender.
Okay, so now you're feeding it in. There's like heat, I guess, involved, pressure involved?
Yeah, it's a combination of heat, pressure, and some secret ingredients on the aluminium.
Always like some black magic here.
Yeah, always a black magic here in this black foil science. And you can look on the back side here, it comes out, and we will Caroline is awaiting the foil, and we will then have a look on it.
The processing will then be much faster, but that will depend on the size of the rollers of the calender then, and you can run faster.
Is there like any speed limit? Like, can you get similar speeds to your electrode production in theory, or?
No, I think we should decouple the processes. It's much safer for
Quality control.
quality.
Interesting.
Thank you. So here you can see the laminated electrode. It really sticks on the aluminium surface, and you can have a look on it. It's now a little bit less pressure. But what I also wanted to show you is that we can also calender electrode on electrode to make electrodes with double thickness. So we can reach up to 8 milliampere hours per square centimeter.
Interesting. So that's how you achieve it. So in your production, you're 4, but then through like the stacking and the kind of combining, get to 8. Okay.
Yeah, you can have a look with the camera. Here I just add a second sheet of electrode, and on both sides.
And that's something also I know in the it's all about calibration, right? You need the right parameters, a bit more pressure. I've seen this also in a lot of other lines, that kind of the tweaking of the parameters is it's really the magic.
Yeah. So this is.
That also happens at the really big lines. I know that.
Yeah.
Constant tweaking. And then also, because I think so now we kind of doing like we're doing an electrode on a copper foil or aluminum foil in this case.
Okay.
On the electrode, now you're putting multiple of them together, and then also I think you can even put your sandwich, right? Is this also how you make it? Or that's already in the extrusion?
Our tri-layer sandwich system can ideally also be laminated this way,
Yeah.
but maybe we do not have to finally, because if we make a lamination process later on with an adhesive, for example, then we do not have to do the lamination. Are you ready?
Are we ready? We start again. So Simon, a thing I also want to show you now is the laminating of additional electrodes, additional cathodes on the current collector with one layer of cathodes. So we can achieve a doubled areal capacity. So in this case it's about 8 milliampere hours per square centimeter per each side, because the electrode can be calendared to itself under the proper conditions.
You can already see it's much thicker now, right, when it comes through?
And you can also then feel it, it's really heavy.
How heavy it is, and also
Strong.
it's getting quite stiff already.
Yeah.
Be patient.
And you can also
Maybe just cut off a piece and
It's still rather hot, I can tell.
yeah, and it sticks, so you cannot peel it off. If I want to peel it off, it breaks, because now the adhesion is really good. And also, if you want to see here, if the calendering is good, you cannot peel it off. You can only break the electrode off, and you can also have a look. It's really 0.5 millimeter thick electrode, and you can feel it. It's already has some decent weight in comparison to the 2 or 3 milliampere per square centimeter electrodes.
Absolutely, and I think, as you say, this is a really proper thickness. Probably then even at some point diffusion limited and things like
Yeah, of course. It's rather maybe a purpose for grid storage, where you are
like energy cell rather than a
rates,
pulsar. Yeah.
below lower than 1, but of course it's
yeah.
additional feature of this process. Yeah.
We've already run this with 1C. That means 8 milliamps per square centimeter. And for this thick electrode, it's, I think, quite good.
Yeah.
Yeah.
And I think that's kind of the next step, because now we have these electrodes.
Yeah.
We made them through all the processes, and now we actually want to see how you're going to test them. And I think the first step is you actually have to put them into a battery form.
Sure.
Let's do that next.
Yeah, let's go and visit the lab and see our cell manufacturing for coin cells and pouch cells, and then later on the cycling systems.
Let's do that.
Yeah, please.
Okay.
So, well, Simon, we are back in our labs, and I will show you how we do the testing. So I've seen how we make the electrodes, and so the standard size is this electrode. So this one, a bigger one with many sticks we've developed with the Austrian Institute of Technology in Vienna, where we had a close collaboration with. But the single-sided pouch cells, also the bipolar stacks, and in the beginning the coin cells we're doing in-house here. And I will show you the glove box, the two guys making the cells here. Yeah, here in the first compartment of the glove box you see Marcus preparing some coin cells. So this is the very first start all the time, where we punch out little circles out of the electrode, either with or without current collector, and then we test them with very small power, and then when we're sure that the electrode material is promising, is good, then we increase the size to pouches, mostly single-sided, but also then double, triple, and so on. And this is the size, the same size we have here. And Helene is now laying this into this sealer, where this will then be lowered, evacuated, and sealed, and then we can take it out from the argon glove box to the environment.
Very cool. Well, that's good to see, and also I think being able to do that, yeah.
Yeah, and we can go now to the cycling room where we have multi-channels for coin cells and also pouch cells,
Yeah.
and also for our higher voltages bipolar stacks.
Let's do that. Let's go.
So please come in. So look over here first. We also have the ability to weld on the clamps, the tabs on the electrodes here. Here you see once again these electrodes, and then the tabs welded on this here for aluminum and for copper. Over here we have then the cyclers. On the left we have 80 channels for our coin cells where we do the cycles, and so we are running many hundred cycles here. You see also a list of all the channels here, of all the experiments, and over here are then the pouch cells. So we clamp them for better performance, and if you turn around, then you can see the cyclers for higher power over there, and here for up to 20 volts where we have our bipolar stacks running here.
Very cool.
And many of these are running now for a couple of thousand cycles here, and we could demonstrate that the technology is also suitable for energy storage in a big scale because it lasts many thousand cycles.
Cool. Awesome. Well, I think it's really good to see, and I think the long-term testing,
Yeah.
and I think I have a quick way to get feedback on the electrode processes
Yeah.
and different materials. Yeah.
That was important for me, because if you go to an external partner every day, then wait 3 months for the results of a coin cell, you cannot do development and scaling up with this technology. Something has to be in-house, and some bigger cells we plan to make outside now to make also some testing on let's say 100 cells, for example.
Brilliant. Awesome. I really appreciate you really showing us the entire journey from, I think, in multiple ways. I think on the one end, from the lab to the scale-up, but also from your slurry all the way down to the cells and the testing. So I think this has been a really nice journey today, and I really want to thank you for showing us around. We really enjoyed it. I think there's only one thing left. If anybody is curious what you do, and I think there's quite a few, because we've seen a lot of interesting innovation. So I would just recommend you, if you're interested, to get in touch with them, either reach out to me, and I'm really happy to get you in touch, or otherwise just find them online at Creonia Cells, but also you can also reach out to Markus Ungerank on LinkedIn, and then hopefully you'll find also some interesting people to connect with.
Yeah, thanks again for having you here. It was a very good day, and I hope I could show you our technology, and that the team supported us so well in showing everything. I'm happy, and yeah, thank you.
Thank you, and really thanks everyone, and hopefully see you very again soon, and good luck till then.